So, amplitude modulation and single sideband modulation. Well, they're both types of amplitude modulation, surprisingly enough, except that AM has two sidebands and a carrier wave, and single sideband has one sideband and no carrier wave. So that's quite easy to understand, isn't it? Say yes, Keith. Oh, you don't think they would have understood from that explanation? Pity. Well, if you didn't understand what I just explained to you, I suppose you'd better watch the rest of this video. Sorry about that. What bits don't you think she understood? At the heart of every radio transmitter there's one of these things, or a circuit similar to this. It doesn't really matter what's in the circuit. There's a transistor and some capacitors and a crystal and such like. But this circuit here, this type of circuit, makes a radio wave. And if I just move the camera a little bit, we'll be able to hear what sort of radio wave it makes. We'll move that over there, and that up there, and move it up. Oh, just got a bit of fiddling around here to do. Let's turn the volume of the radio receiver up. And we'll connect a battery to the oscillator. If you can see that there. Well, that's a bit loud, isn't it? So whenever I connect the battery to this little oscillating circuit, it makes a radio wave. And we can actually see the S meter coming up here on the scale. But unfortunately, a radio wave in itself doesn't tell us very much information. Listen. Well, it's really rather boring and not much use to us. And that's why when radio waves or Hertzonian waves were first discovered, they weren't considered to be very important or very significant. And it wasn't until the idea of combining them with Samuel Morse's idea of breaking up letters of the alphabet into a code, as we just heard there, or my feeble attempts at Morse code anyway, and then the letters of the words could be spelt out. But that's very cumbersome and needed trained people to operate. Much better, it was thought, if, like a telephone that had been invented recently at the time, you could just speak into it and your voice could be heard over many thousands of miles, that the radio wave would carry your voice. And that's what's generally known as modulation. And that's where our story about amplitude modulation begins. So what we were just doing was listening to a radio wave. If we could see it, this is what a radio wave would look like. This device here is called an oscilloscope, and we needn't worry too much about oscilloscopes, but it's, if you will, drawing a picture of a radio wave. This particular radio wave is at 1.36 megahertz. Now, the things to note about this particular radio wave: it's an alternating current. And if you can see the center line, the center horizontal line here, that represents the middle of the radio wave. And the distance from the middle of the radio wave to the top of the signal, to the top of the radio wave, and or from the middle of the radio wave to the bottom, is known as the radio wave's amplitude. This is the amplitude of a radio wave. Now, the curious thing, or not the curious thing, the interesting thing to note is that the tops of the amplitude and the bottoms of the amplitude are straight. It's a straight, pretty much a straight line right across the top of the amplitude and the bottom. The top of the radio wave and the bottom of the radio wave aren't varying at all in their height. Their amplitude isn't changing, it's not varying. It's the same. And that constant sound that we were hearing, the continuous sound, the very boring sound, is because the top of this radio wave is constant. It's flat, it's not varying at all. That's significant. Just bear it in mind for a moment while we move to the next stage. I want you to imagine that this here is the carrier wave. This is the single monotone sounding thing that comes out of an oscillator. And okay, I've been rather lazy. I haven't drawn all the oscillations all the way down this piece of card. That's because I'm not very patient. So just imagine this is the carrier wave that we saw that used to be broken up into dots and dashes to form Morse code. This is the carrier wave, this is the signal that goes into the modulator. But along with it comes at a much lower frequency an audio wave. This we'll pretend is the sound of my voice. It's a much lower frequency measured in kilohertz, whereas the radio wave is normally measured in megahertz. And what happens is that when they come out of the mixer, the sound of my voice has been superimposed on the amplitude of the carrier wave. So what comes out is this. If I can just move the pieces of cardboard away, it comes out like this. And you may notice that the sound of my voice, by sheer not good luck but design of course, fits exactly, or with almost exactly, the shape of the modulation of the carrier wave. So this carrier wave has been converted into that carrier wave. And there's my voice, my audio signal, the sound of my voice on the top. Now it turns out that if you modulate, when you put it into a modulator, you don't just modulate the top of the radio wave, you also, by the function of the modulator, modulate the lower part of the radio wave as well. And this lower part is an exact image of the top part. This radio wave is being amplitude modulated. You can kind of see the radio wave, but the tops and bottoms of the radio wave are going up and down in exact sympathy with the sound of my voice. So this is what an amplitude modulated radio wave would look like. And you see that the amplitude is constantly varying. In other words, it is being modulated by my voice. The radio wave, sometimes called the carrier wave, is being modulated, changed by the energy coming from my voice. So there are two actual signals here. One is the radio wave and one is the shape of my voice. You see? No voice, no modulation. Now, for your exam, you may need to know that amplitude modulation is known as, if I can pick the piece of paper up, A3E. That's its technical classification, if you can see it. Not the best lighting in here, I have to admit. A3E equals amplitude modulation. And that's what amplitude modulated radio wave looks like. But we need to know a little bit more about it. This audio signal, which I've explained to you, is on the top and the bottom of the amplitude modulated radio wave, is known as the modulation envelope. There, that's been typed out, so that looks much easier to see, doesn't it? So these up and down fluctuations, the modulation of the amplitude, represent what's known as the modulation envelope. And the radio wave has two distinct, well actually it has three parts to it. From the centre upwards, it's known as the upper sideband. So from the centre to the top of the amplitude at any one point, it forms the upper sideband. And as you may well suspect, and I seem to have lost a piece of paper, no, as you may well suspect, the lower part of the amplitude modulated signal is known as the lower sideband. So there's the upper sideband and there's the lower sideband, and in the middle there is the carrier wave, which should go all the way down here, but I'm just too lazy to draw it out for you. If we wanted to, of course, we could, for reasons of efficiency, knock out some of what we're seeing here, because the lower sideband contains exactly the same information, it contains exactly the same sound as my voice as the upper sideband. So in the interests of efficiency, we could cleverly and technically wipe out the lower sideband and just transmit the upper sideband. The information here is exactly the same, whether it's upper or lower sideband. In addition to that, the carrier wave no longer serves any real purpose, so we could get rid of the carrier wave as well. And if we did that and produced what's generally known as an SSB, or upper or lower sideband, single sideband radio transmission, what we would end up with is what is technically called a J3E signal, a single sideband with and a suppressed carrier wave. So single sideband, whether it's upper or lower sideband transmissions, known as J3E, is a single sideband and suppressed carrier wave. That's much more efficient. You can concentrate nearly 4 times as much power just into the signal that you want to send, rather than sending a duplication, both sidebands, as you would do in an amplitude modulated signal. So, that's easier to understand, isn't it? Say yes, Keith.